Okay, so if we go over what we were doing in our last lecture, okay, we are basically looking at the canonical ensemble now. Our system can exchange energy. The energy is not fixed, so it is fluctuating, and then we studied what is the fluctuation in this energy, because we will be making definite statements about our system, but if the energy is constantly changing, our statements won't be so definite. And what we figured out was that the relative fluctuation in the energy was given as 1 over the square root of the number of particles we have in our system. So for a macroscopic system, which has of the order of 10 to the power 23 particles, the relative fluctuations is negligible. It's the fluctuation in the energy is of the order of 1 part in 10 billion. And our devices won't be so precise to measure such a small fluctuation anyway, so we won't be able to measure a significant fluctuation. Then we looked at the ideal gas in the canonical ensemble. We saw that since we can just basically write the n-particle partition function in terms of the one single particle partition function, so the computation was much more simpler, and of course we recovered the same result as before. And in fact, since the energy fluctuations are negligible, you can basically say that nothing should change if you fix the energy. But if you fix the energy, then you recover the canonical ensemble. So the canonical ensemble and the microcanonical ensemble, they should give you the same answer. And in fact, if you did check it out, we calculated the entropy in the canonical ensemble. Well, we obtained this relation, which was the same relation in the canonical and the microcanonical ensemble. If you, for energy given as p squared over 2m, we calculated the entropy. If you compare this expression of the entropy with the expression we obtained in the microcanonical ensemble, would be in fact identical, with the identification that energy is equal to 3 over 2 nkt. Remember, in the microcanonical ensemble, we have energy as our parameter. In the canonical ensemble, we have the temperature as our parameter. So the entropy expressions that we derive in both of them will have different arguments. In the microcanonical ensemble, the entropy expression we have is a function of NV and E, whereas in the canonical ensemble, the entropy is a function of NV and T. But we know how the average energy and T is related. If you replace the energy with the average energy in the microcanonical ensemble, then the results are identical. So basically, that's a result of the fact that the fluctuations are negligible. And then we were looking at, well, okay, why the fluctuations were negligible, because we will see many examples where this probability distribution is actually very peaked, almost a Dirac delta function. The width is the fluctuation. And then we looked at the problem in the canonical ensemble, in the ensemble theory. We had all these copies, and then, well, in the book, the derivation is slightly different. The derivation I have here is what the book uses towards the end of the quantum particles, but the results are basically the same. I have my copy. I consider the microstates of my system into very almost degenerate states. I just group them into cells, and then I ask myself the question, if I have, let's say if NR denotes the number of copies in my ensemble in the Rth microstate, then NR is what I'm actually interested in. Eventually, I will be asking the question, if I picked one member of my ensemble randomly, what is the probability that it will be in the Rth microstate? That is what I'm interested in. That's what I need to know in order to be able to calculate the ensemble average. And then we looked at the most okay, so this is, since there are GR states in each cell, I can just distribute these NR copies in GR to the NR different ways within this cell. But just shuffling the particles among themselves doesn't give me a new ensemble, so that's why I'm dividing with NR prime. So this is the number of ways I can create an ensemble corresponding to these numbers NR. And then I asked the question, okay, what is the maximum value of omega? That will give me the most probable distribution numbers NR. And then we obtain, then we obtain that NR star, or that probability to be a function of ER only, and the probability that my one copy I choose in my ensemble to be in a particular microstate R will be e to power minus beta ER over Z. And, well, which was basically the expression we had also derived before by just treating my system and the environment as an isolated system and using microcanonical ensemble. And that was where we had left. And today I would like, that is in the first hour, ask this question. Okay, this is the most probable numbers. These are, NR star is the most probable number, which gives me this probability. What about the average values of this NR? What's the average number of copies in my ensemble that are in the microstate R? And since in general the probability distributions will have this behavior, the most probable value and the average value, I expect them to be equal. The fluctuations will be negligible. Now that is a nice exercise in mathematical physics. In fact, that is why I would like to at least go over the main steps to actually show that the average value is equal to the most probable value. So for that, I need this omega n r's. Okay, this is my omega n r. Now, I would like to calculate NR, or let me say NS, the number of copies in the microstate S. This will be equal to, well, sum over all possible sets. And I have this many of each one of them. And the value of NS in each one of them is NS, and divide by sum over all possible sets of just omega n r. This is basically the average. So let me write these omegas explicitly. Let me just keep it omega n r. You see, that product, this product over here, contains the product over all microstates. I'm just multiplying it with just the number of copies in a particular microstate S, NS. Now, I can do a trick. You see, among all those terms in the product, in the expression of omega nr, there is one gs to the power ns. And I'm multiplying this one with ns. But this is nothing but derivative with respect to gs of gs to the power ns. If I take that derivative, it will bring down a factor of ns, and the power of gs will be reduced by 1. So let me multiply by gs. So I have such an equality. So the average of ns would be equal to sum over all such possible sets, gs times derivative with respect to gs of the product of this factor, divided by sum over nr omega nr. But now that gs times the derivative with respect to gs it doesn't depend on my summation. I can just take it out. So this will be equal to 1 over so I have that function, that sum of omega n r. I'm taking its derivative and dividing by itself. Now that's nothing but the derivative of the logarithm. So ns is actually gs derivative with respect to gs of logarithm of So if I would like to calculate the average value of ns, it's enough that I calculate that sum. If I know that sum, then I just take the logarithm and take the derivative, and I'm done. Now, what is that sum? Now, basically, I have this set of integers. And in that set, there are infinitely many elements. But the integers in that set satisfy these conditions. If I sum all the integers, I should get the number of copies in my ensemble. And furthermore, if I multiply an R with ER and sum them all up, I should get n times the average energy. So I'm basically making that, carrying out that sum subject to these constraints. So let me ask you this question. What is a plus b plus c, let's say, to the power n? How can you write this? Let me start with a simpler one. A plus b to the power n. Just binomial expansion. Do you remember the explicit expression? Let me write it in this way. A to the power n1, b to the power n2, n factorial divided by n1 factorial times n2 factorial. I sum over all n1 and n2 from 0 up to infinity, subject to the condition that n1 plus n2 should be equal to n. Or you probably have seen this this more familiar form of this. I select n1 from n, and then I have a to the power n1, b to the power n minus n1. And n1 goes from 0 up to n. The expression on the right is probably the one that you are more familiar with. But the expression in the middle is the one that can be more easily generalized to 3, 4, or 5 terms. So if you have, let's say, a1 plus a2 plus a3 plus raised to the power, let's say, n, this you can always write as a summation over integers ni. Now, ai to the power ni over ni factorial, now you say a to the power n1 divided by n1 factorial, b to the power n2 divided by n2 factorial. So each one of these terms raised to some integer power divided by the same integer factorial. Of course, there's such a factor for all of the AIs. And there is also n factorial here, this n factorial. And then, of course, these integers satisfy the condition that the sum of all these powers of ai's should be equal to n. Now, if you compare it with this expression over here, they somewhat look similar. There is one important difference, though. These integers and r satisfy one additional constraint. You see, if this constraint were not there, then we already know how to sum that. But I have that additional constraint. I restrict the sum of nr times er to a particular value. Now, if I only keep the first constraint, that sum over nr is equal to the number of copies in my ensemble, then the sum of nr er can take any value, not just that value. So I would rather have a sum in which that sum in the second line can take any value. So I will do that. I will do the trick. You see, I have this thing. Subject to the conditions. This is what I'm trying to calculate. But I would like to remove that constraint over u. So let me sum over u. You see, this constraint restricts the possible values of u. But if I sum over all possible values of u, effectively I'm removing that second constraint in my summation. But that's not what I want. I want to somehow find the value of that summation for a particular value of u. I should be able to pick, once I evaluate the sum, I would like to pick up the sum corresponding to a given value of u. Well, let me just multiply all of this thing with g to the power nu. So different values of u will correspond to different powers of z. So if I can evaluate this sum as a function of z, I make a Taylor expansion or a polynomial expansion in z. Depending on the power of z, I know which the coefficient of that power of z will each correspond to different values of u. So this, I'm effectively, rather than calculating this sum directly, this sum over here, rather than calculating this sum directly, I'm now trying to calculate a generating function of that sum. In your mathematical physics course, you have probably seen generating functions. This is a generating function of that sum that I'm interested in. Well, let's see. This is equal to, remember, nu is this sum. So that term is actually this one, sum over all nr, with the condition that nr is equal to n. You see, since I'm already summing over all values of u, I don't impose the second constraint, because if I remove that second constraint, I already have the other summation over u, all possible values of u. Product over r of gr to the power nr z to the power er. Remember, nu is sum over nr er. So z to the power nu, no, z to the power, that sum is the product of z to the power nr er. I can just put it over here, sorry. To the power nr. When I calculate that product, I already have z to the power sum over nr er. That is z to the power nu. Divided by nr factorial. But this is nothing but Now I know how to carry out that sum. Let me give some names to some function. Let me call this sum f. This is a function of g, no, f of n and u. This is my g. This is a function of n and z. So now I know what g is. But this is nothing but sum over all values of u, f and u, z to the power nu. Now my task is now to determine the coefficient of z to the power nu in the expansion of g. That is what f is, what I'm interested in is. Okay, so we have now used, we have used the polynomial expansion. You see, this sum, this step from here to here, is the general expression of the polynomial expansion of a sum of terms to raise to some power. We use the concept of the generating function. So we are interested in this one. So we are just multiplying with some factor that we can use to identify the coefficient of and summing over that u. We use the generating function. Now we have to consider an expansion of g in terms of some powers of z, and we have to pick up the coefficient of z to the power nu. Well, that is what Cauchy's integral formula is for. You say f of nu would be dz g and z divided by z to the power nu plus 1 around the loop around z equal to 0. 1 over 2 pi I. Because that integral would be just 2 pi I times the residue at z is equal to 0. But the residue at z is equal to 0 is the coefficient of 1 over z. Well, since I'm dividing by z to the power nu plus 1, the coefficient of 1 over z in this integrand is just f of nu.
I don't get this part, honestly. I've done this like a couple of times myself as well, and it just seems to be a little complicated.
Well, you see, dz over z to the power n. This is just 2 pi I times 0 if n is not equal to minus 1. And 1 if n is equal to minus 1. So what is g? We know this is the expansion of g. Let me just call this prime. So g of nz over z to the power nu plus 1. This is 1 over z to the power nu plus 1. Sum over all u prime, f of n u prime, z to the power n u prime, which is u prime f of n u prime 1 over z to the power n u minus u prime plus 1. You see, when you evaluate the integral over z of g of nz over z to the power nu plus 1. This will be 2 pi I. It's almost all the u primes will give 0. Except that the one u prime is equal to u. Because when u prime is equal to u, that factor over here is just 1 over z. That's the only one that will contribute. 2 pi I times sum over u prime f of n u prime Kronecker delta u prime. You see, this I can write as 2 pi I Kronecker delta n1. If n is 1, it is 2 pi I. If n is different than 1, that is 0. Same thing over here. N is equal to 1 means this exponent is 1, but that means u and u prime are equal. So this will just give me 2 pi I times f of n u prime. Okay, I cheated somehow. You see, this assumes that n is an integer. Because if n is not an integer, z to the 1 over z to the n has branch cuts that start at 0. So I have to make sure that n is an integer. But to make sure that n is an integer, I have to make sure somehow that u prime is an integer. But I didn't specify an energy unit. If I choose a sufficiently small energy unit, let's go back. Okay, so here, what I actually need are ER, the energies of the microstates have to be integers. If I haven't specified any energy unit, I have to be measuring these ERs in terms of a unit of energy. If I choose a sufficiently small unit of energy, then all the energy levels will be some integer multiple of that unit of energy. So although I am assuming that ERs are integer, that's not a loss of generality because I'm free to choose my unit of energy. And since I'm measuring all the energies in terms of that particular unit, ERs are integers. They don't have any unit. They don't have any dimension. ERs will be just integers. And the actual energy will be that integer multiplied by whatever energy unit I chose. So if I just summarize, I'm taking a very long way to drive my result, but that's the only way kind of that we can. So what we did, well, we are trying to calculate this sum over here. I cannot calculate it directly. That sum is this one. And the reason why I'm unable to calculate is the second condition, that the sum of NR, ER should also be fixed. I can remove that condition by using a generating function. I'm just summing over all allowed values of U. That's my generating function. But if I sum over all values of U, I can obtain the result. I know the result. Oops, where did I write it? Yeah, this is my G. If I sum over U, I know the result. But I don't want the summation over U. I want a particular term in that summation. And in order to do that, I can use the residue theorem. So since I want to find the coefficient of nu, z to the nu, I just divide this function g by z to the power nu plus 1. If I integrate over, the residue will be what I'm looking for. Now I need to calculate that residue somehow. Of course, I'm not looking for an exact solution, and a good enough approximation would be enough for me. So this is what I'm trying to calculate. F nu is actually equal to 1 over 2 pi I dz around the loop of sum over r g r z to the power e r to the power n divided by z to the power nu plus 1. Now let me look at this one. I can even assume the ground state to have zero energy. So G0 is just G0. Z to the 0 is 1. Plus the first state, Z to the E1, plus G2, Z to the power E2. And keep in mind that these E1s, E2s are just integers. Raised to the power n. In fact, I can even consider dividing everything by G0 to the n. So that, let me put hats over here. Gr hat is actually Gr divided by G0. So these are all hats. Now why I want this to be 1? Yeah, because it will be nice, because when z is equal to 0, this function is 1. That function starts from 1. Now, as I increase z, it becomes larger than 1, but remember that capital N is a huge number. So it increases very fast. Let's look at this function. This is sum over r gr hat z to the power er. Now let's look at this other function, 1 over z to the power nu plus 1. You see, this gr times z to the power e of r increases exponentially fast. And for large values of z, it diverges. 1 over z to the power nu plus 1, when z is equal to 0, it diverges. But as z increases, it decreases very fast. With z, it almost goes to infinity immediately for non-zero values of z along the real line. So what this tells me is this function I have this function over here. It diverges for when z is equal to 0 because of that 1 over z to the power nu plus 1. It diverges for large values of z because the exponent diverges, because the numerator diverges. And it diverges much faster than the 1 over z, z to the nu plus 1. So the ratio diverges for very large values of z. I don't know how the function behaves, but I know that at some point there is a minimum point. So this is the function that I'm actually trying to evaluate. And keep in mind that this, I'm kind of exaggerating the width. It is very narrow. So I'm integrating some function in the complex z plane. But when I look at its behavior along the real axis, I see that there is, along the real z-axis, there is a point where it has a minimum value. And at the origin, it diverges. For larger values of z, it diverges. But around the, along somewhere, there is some minimum value. Let me just call that x0 star. This is along the real line. Now we use some complex calculus. So what do you remember about analytic functions of complex variables? What do you remember? Yeah, they satisfy the Cauchy conditions, but they imply something about the maximum or the minimum values. there are no extremum values. You cannot have a local maximum, you cannot have a local minimum of a function of a complex variable. If you have a function of z only, not z star, so it has to be so-called holomorphic and analytic, it cannot have a local extremum. It cannot have a maximum, it cannot have a minimum. At most, it can have saddle points, which means that saddle points mean that if it's a minimum along one direction, it has to be a maximum in some other direction. So what does this tell me? So if I would imagine this function in the complex plane, we had just seen that it has a maximum value, it has a minimum along the real axis. But then that minimum is not a global minimum, it's just a saddle point in the complex plane. It has such a behavior.
Can say that it will satisfy the Laplace equation.
Yeah, sure. It will. I mean, the real part, imaginary parts, they both satisfy the Laplace equation. This is a holomorphic function, analytic function of Z. So it's a nice function of the complex variable Z. So it satisfies all the required conditions for this theorem. Now let me look at the imaginary Z, real Z plane. This is where I have x0 star. And this function has a saddle point around x0 star, and furthermore, I need to evaluate a loop integral in the complex plane that contains the Z. What will be my loop? Well, it can be arbitrary. Of course, I'm making the assumption that the only pole this function has is at z equal to 0. But you see, it's just a polynomial. The sum over r, gr hat z to the power e1 raised to the power capital N is a polynomial of a huge degree, but a polynomial. Polynomial doesn't have any poles. The only pole is due to 1 over z to the power nu plus 1, and that pole is at the origin. So I can choose any loop around the origin. Well, I can choose this loop. The important thing is I'm going in this direction at x0 star. Why? Because if I choose such a loop, this function has a maximum value on this loop at the point x0 star. So basically what I will be doing is 1 over 2 pi I dz I'm integrating over a loop that passes through x0 star. Let me call this whole thing h of z, or e to the power h of z. Or even minus h of z. Now, I will do some more tricks. You see, x0 along this loop is a maximum. The main contribution will be from this region to that loop. So I can even do one more thing. Let me just imagine I just extend this loop to a loop that goes to infinity. I will be integrating not around that loop, I will be integrating along this line.
Will you use Laplace
Hmm?
transformation?
No, I won't do any law. I will just convert this to a Gaussian. You see, along that line, it has a maximum at x0 star. H of z has a minimum around x0 star. So h of z will be h of x0 star plus h prime, of course, along this line at x0 star times z minus x0 star plus h double prime of x0 star z minus x0 star squared over 2 factorial plus higher order terms. So this e to the power minus hz will be e to the power minus h x0 star. Well, that is basically the value at that point of this function times, this is 0 because it's a maximum. Along that line, x0 star is the maximum or minimum, extremum. And then I have e to the power times e to the power minus h double prime x0 star z minus x0 star squared divided by 2 factorial plus other terms.
That should be plus.
No, you see there's a minus over here. So that's the minus.
I mean, between exponentials.
No, they are multiplied. You see, I have all these terms are added in the exponent.
Okay.
So it's the product of whatever I have in the exponent. But now this integral this is equal to e to the power minus h x0 star. Then I have a Gaussian integral there. 1 over 2 pi I divided by 2 pi square root of 2 pi divided by h second derivative at x0 star. Well, to see this, I need to make a change of variables. You see, just write z is equal to x0 star plus I y. So dz is equal to I dy. This I cancels that I. And as I move along this line, y changes from minus infinity to infinity. That gives me the Gaussian integral. Okay, I won't do the rest of the computation. But you have to identify x0 star with e to the power minus beta. But x0 star is just a constant. You just express it as beta. You have to go ahead and calculate all these things. I know what this function is. But eventually what you will obtain is exactly the same result as the maximum value of n0 star. I would rather skip the algebra. But the nice thing is, you see, you have seen all these techniques in your mathematical methods courses. So you see that you're actually using a significant number of them in just trying to answer this one problem. Any questions? No, I personally will not spend more time on this derivation. I will not ask you for such a derivation, but I think this is something you should see once. So let's give a break now, and we will continue after the break.